Ideal gases were introduced in an earlier video. When dealing with ideal gases and assuming ideal behavior, it is useful to have a standard set of conditions. STP refers to standard temperature and pressure, where the standard temperature is 0 Celsius or 273.15 Kelvin, and the standard pressure is 1 atmosphere. Let's use the ideal gas law to solve for the volume of 1 mole of ideal gas at STP. Interestingly, we see that 1 mole of ideal gas at STP is equal to 22.4 liters of volume. This is a useful conversion we'll use often when dealing with densities of gases or gas phase stoichiometry at STP. When we introduce the ideal gas law, we notice that this equation is a good approximation for any gas behaving ideally. That is to say, at high temperatures and low pressures. But if all gases behave ideally under these conditions, how can we differentiate between gases? The answer is knowing the density of the gas. Let's recall that the molar mass is grams per mole. Let's multiply both sides by the moles and divide both sides by the molar mass. Notice the terms canceling leaves us with moles equals grams over molar mass. Let's go back to the ideal gas law and substitute the moles term into the ideal gas law. Here's our equation. Now, let's multiply both sides by the molar mass and divide both sides by PV. Here is the final equation. Notice that the mass in grams over the volume in liters is the density of the gas. We can rewrite this equation in terms of the density. So here it is. We can identify the gas based on its molar mass, so long as we know the gas's density at some temperature and pressure. Here's an example of a problem that's typical in every general chemistry class. 6.16 grams of an unknown gas at STP occupies a 3.0 liter cylinder. Identify the gas. Oftentimes, this will be a multiple choice question, so I've listed some gases. Assuming ideal behavior at STP, we can use the molar mass of the gas to identify it. Notice the temperature and pressure are given in the problem, STP. And while we're not explicitly provided the density of the gas, we are provided the mass of the gas and the volume of the cylinder which it occupies. I'll insert my standard temperature and pressure and find the molar mass of the unknown gas is 46 grams per mole. This molar mass matches really well with the molar mass of answer A, nitrogen dioxide. An unknown homonuclear diatomic gas, X2, at 25 degrees Celsius and 1.5 atmospheres is found to have a density of 1.96 grams per liter. Identify the gas. First, homonuclear diatomic means that there are two atoms of the same element that make up the diatomic gas. Since the density is provided, I can use the molar mass equation for this gas. Next, we can assume ideal behavior at temperatures of 25 Celsius, which I can convert to Kelvin, and a pressure of 1.5 atmospheres. Inserting my values gives a molar mass of 32 grams per mole. to two significant figures. Since the gas is diatomic and 32 grams per mole, this means that each element must be 16 grams per mole. This is oxygen. Oxygen gas, O2, is the unknown gas. Consider the reaction of potassium chlorate decomposing to yield potassium chloride and oxygen gas. How many liters of oxygen can be produced from 4.80 grams of potassium chlorate if the reaction is carried out at standard conditions, or STP? This is a stoichiometry problem because the question is asking to find the relationship between species in the balanced equation. We want to find the liters of gas produced from a reactant. The goal is to convert potassium chlorate to oxygen gas using the mole-to-mole ratio. Also, we are told that the reaction occurs at standard conditions, or STP. At STP, we can use 1 mole equals 22.4 liters to convert moles of gas to liters of gas. First, I'll convert the mass of potassium chlorate to moles of potassium chlorate using the molar mass. Next, I'll convert the moles of potassium chlorate to the moles of oxygen gas using the mole ratio from the balanced equation. Finally, I'll take advantage of the STP conditions and use the ratio 22.4 liters per mole of ideal gas to convert the moles of oxygen to liters of oxygen gas. There are 1.32 liters of oxygen gas produced. Consider the reaction of calcium hydride reacting with water to yield calcium hydroxide and hydrogen gas. How many grams of calcium hydride are needed to produce 76.8 liters of hydrogen gas at a pressure of 0.750 atmospheres and a temperature of 25 degrees Celsius? Here, we're being asked to produce 76.8 liters of hydrogen gas, but we need to find the mass in grams of the reactant, calcium hydride, needed. The goal is to convert hydrogen gas to calcium hydride using the mole-to-mole ratio. Note that the reaction does not occur under standard conditions. Therefore, we must use the ideal gas law to find the moles of hydrogen gas first. I can find moles by dividing both sides of the ideal gas law by RT. Notice the only conversion is the temperature conversion, which has been converted to Kelvin here. Under these conditions, 76.8 liters of hydrogen gas is equal to 2.36 moles of gas. Next, I have to convert to the mass of calcium hydride. In the first step, moles of hydrogen are converted to moles of calcium hydride. In the second step, moles of calcium hydride are converted to grams of calcium hydride using the molar mass. 99.4 grams of calcium hydride is required to yield 76.8 liters of hydrogen gas at 0.750 atmospheres of pressure and 25 Celsius.